Hello and welcome to another episode of Envisioneering Exchange, the podcast where industry leaders discuss the most important topics in HVACR. I'm your host, John Sheff, Danfoss's Director of Public and Industry Affairs. Now, you can subscribe to our show on Apple Podcasts, Spotify, SoundCloud, or wherever it is you get your podcasts. Today, we're going to be discussing hydronics again, and specifically what's going on in the Baltimore, Washington market, and a specific project called the Towson Courthouse Project that my guest, Jay Chan, who was in our previous episode, is currently working on. Now, if you haven't listened to the last episode, I highly recommend you go back and take a listen because Jay and I delve into all the particulars dealing with hydronics, which is a complex and not well understood technology. So please do that. But if not, we're going to give you a quick recap. Jay, why don't you tell us a little bit about yourself, about Chesapeake, and what you do there?
Sure. Thanks, John. So I am the Director of Strategic Markets for Chesapeake Systems. I have been involved in the commercial HVAC market for 30 plus years. I started in the field working on building automation systems, and I saw the transition, or primarily I was brought in for the transition from pneumatic controls to analog electronics and to where we are today with DDC controls. At that point, I took an interest in the mechanical systems and decided to go back to school for a mechanical engineering degree. From there, I went to work for a consulting firm as a mechanical design engineer, designing mechanical systems for primarily commercial office spaces, laboratories, some specialized industrial process facilities, clean rooms, and labs as well. So from there, later moving into sales, I went to work for a rep firm that specialized in hydronic products. And that's where I've developed most of my hydronic experiences. When you get a chance to focus on hydronics only, you tend to become pretty good at it, let's say. So I also work for a global manufacturing company who specializes in climate and energy, which is Danfoss, by the way. And so now I work for Chesapeake Systems. And my role there is to work directly with owners, focusing on what we call the strategic markets: schools, government, hospitals, institutional accounts, and some large property management firms. And what we identified early on with working with owners is just the fact that, we start projects where the owner has a concept or, vision. And then once it goes through the pinball machine of design, bid, equipment awards, installation, and commissioning, the owner tends not to get what he had envisioned, or a building that doesn't perform the way he had expected it to. A lot of that has to do with the fact that pinball machine being an engineer who designs based off the interpretation of what the owner wanted, a contractor that was awarded based on low bid by his interpretation of that design, and then the equipment vendor who supplied the packages for the equipment based on their interpretation. And so, by the time we go through all of this, sometimes, the owner gets what he's asked for and it performs well. But in most cases, there are issues.
And I won't get into, again, like I did last episode, how much I love Chesapeake and what they're doing, but there are not a lot of rep firms who are doing what Chesapeake is doing and has somebody like Jay who's really out there trying to make sure that end users are getting what they want and their problems are getting solved, and trying to break that supply chain a little bit that bounces these projects all the way down the line until sometimes they're not really recognizable from where they started. So, Jay, before we get into the Towson Courthouse project and what you're seeing in the Baltimore, Washington market, give us a quick recap of hydronics and what these systems look like and why it's so important to have a well-functioning balanced system.
Sure. Hydronics, to me, is where we remove or add heat to the system through a means of water. The water is a great medium for heat transfer, and that's why we use it today. However, balancing becomes very important because we know that the function of BTUs, or heat removed or added, is directly related to the amount of flow that we provide. So, these systems consist of pumps that move water through the system, chillers that remove the heat from that water in the summertime, boilers that add the heat to the water in the wintertime, and all leading to what we feel today, and that's through the air, and that's through the coils and the air handling units, fan coil units, VAVs, and all of that relies on the proper amount of flow. Otherwise, you don't get the proper heat transfer. And so balancing is very important. In many of these cases, we don't see the proper balancing, and it does tend to lead to a lot of issues in the buildings.
And yeah, so the concept of balancing of having too much water overflow in some of the coils, not enough, or underflow in some of the other ones leads to poor heat transfer. It can manifest itself in poor temperature control, so discomfort in some of the rooms of the building. Some rooms could be too hot, some rooms could be too cold, but then also some more serious issues like way too much humidity and mold that can really make people sick or make the building so uncomfortable that it cannot be occupied, and causing a real headache for building owners. So a lot of consequences there for a sick and imbalanced building. And so getting into those sick buildings, we're going to talk about the Towson Courthouse project, which is a project that Jay and I actually worked on and Jay is still working on. And this was one such building located in Towson, Maryland, and owned by the state. Jay, why don't you introduce the building, where it is, when it was built, who the end user is, and how you first got into the project?
Sure. The project is located in Towson, Maryland. It was built in the early 90s. The state eventually ended up taking over the facility at some point and then became managed by Maryland Department of General Services. We had gone in and presented the marketing plan that was put together by Danfoss and supported by some of our other manufacturers that we represent. Again, creating that comprehensive solutions package for hydronic systems. And the presentation went well, and it was well received. And afterwards, it was clear that we needed to look at several projects where they had significant issues with temperature control and humidities. And so the Towson project was one of these that we decided to take this comprehensive approach and look at. So the project has been ongoing. Right now, we are pretty much, I'd say, 3/4 of the way through. When we first did our initial walkthrough through the project, there were issues of water, humidity, and from what we could tell, it was going back to what we talked about in an earlier podcast of having facilities engineers who want to take pride in what they do, but they're not properly educated or trained in some of these complex systems. So they don't call contractors that may know or understand these systems and hydronic systems better. So they try to take it upon themselves to try to make tweaks and changes. Well, that was part of what cascaded into further damage over long periods of operation under those conditions. And equipment failure started to occur. We had water issues, we had humidity issues, temperature control issues. So eventually we decided to look at replacing this building and looking at it as a new comprehensive approach to a new design with high efficiency equipment and utilizing the best practices that we went into discuss regarding the hydronic loop.
It's really interesting, this project, because it's extreme in some parts, and I'm going to ask you, to describe exactly what was going on with the building, but it's also typical because, like you said, I think that, over the years, these facility managers whose, job it is to take care of these buildings and, like you said, take a lot of pride in the work, but are just not properly trained, they start making tweaks. They don't understand the system. They think they have a chiller problem. They think they have a pump problem. And, they're making adjustments to try to correct one symptom, not realizing that it's really part of a larger problem. And so when you got to this building, what was going on with it, Jay? What were the symptoms? Because I know a large part of it couldn't be used, right?
Correct. One of the big things that we noticed was that usually in the mechanical rooms, we have exhaust fans. They either run continuously or they run based on off based on the temperature in those spaces. They have a relief damper or an opening that whenever the fan runs, that damper opens up and to make that a net pressure neutral condition. So they had those dampers closed, thinking that they were providing or bringing in heat into the building. So that caused the building to go further negative, in addition to the tweaks to the air handling units, where they were actually, disabling and closing outdoor air openings, which further drove the building negative. So they had major infiltration problems. On top of that, there were tweaks made to the valves where they were opened because they thought they weren't getting enough cooling. So they would open these valves, the manual balancing valves, and we were overflowing coils. So it was a cascade of all these different issues that eventually, caused major equipment problems.
Yeah, so they were basically sucking hot air in and then overcompensating by turning the valves way open.
Correct.
And so what ultimately happened?
So eventually the chiller started to have issues. The pumps were over pumping. There were certain areas over certain courtrooms where, since the balancing valves were opened too much or throttled down too tight, that they were hearing water noise. It literally, at some places, it sounded like marbles just rolling through the pipe over the courtrooms.
And so, Jay, the judges were complaining that they could hear something up above them when they thought was marbles rolling around. And it was really the water making that sound up in the pipes. And, at some point, a whole wing of the building got so humid and damp that it was unusable, right?
That's correct. What was happening is that the building was so negative and pulling in so much outside air that the whole building became so humid that the condensate drain pan and the air handling units were actually collecting water and leaking in the ceiling tiles. So those areas, became unusable, or they had to move people out of those areas.
Had DGS, the Department of General Services, tried to fix this building before? Were you the first one to try to help them address it? I mean, what was their process here?
I'm sure they had. They had asked me to look at the building because of some of these issues. And so, walking through, it took multiple visits to really dig into the original design. We pulled the original design drawings to make sure that the capacities were correct, and it looks like the original design was feasible and functional, and was properly sized as far as equipment went. However, like I said, most of it was that the tinkering of certain things that weren't functioning properly, and just which cascaded into or manifested into much larger problems.
Yeah, so this is just user error over a number of years, causing these systems to get way out of whack. So, what did you propose to fix this problem? Was it one big project? Were you adding pieces over time? What was the initial proposal?
Sure. The initial proposal was to go in and look at balancing, to change and tweak controls so that we were maintaining a positive building pressure as opposed to a negative building pressure, first of all. The second was to balance the hydronic system so that, we put the pumps back into performance where they should have been originally. However, as we started to move through, we realized that some of the equipment or some of the main components to the building were kind of reaching end of life, or were having enough issues that we thought they needed to be replaced. So as we continued to move forward and evaluate all that, it just became a project that they wanted to look at setting a new gold standard based off of the synchronized hydronic loop, to create a building where we looked at the whole entire system, applying, the best practices of energy savings and principles.
And yeah, I think that's what's really exciting for us is that, even though this project was not the biggest project, it really was something that DGS is going to use as a blueprint going forward for some of their other buildings. So, give us an overview of what the project turned into. What are the technologies that you're applying, and how are you installing them?
Sure. So let's start off with the chillers. The chillers, we're using modular chillers. So instead of one large chiller, it's we're using a modular approach so that we get better part load efficiencies. The other thing is that the chiller has a heat rejection capability, so we're using that for the shoulder months, so that when there is heat available in the system, and there's a somewhat of a small heating requirement, we're able to reject heat so that the boilers don't have to run. On the pump side of it, we used the design envelope designed by Armstrong Pumps, where it's a concept of sensorless pumping, and that is to utilize the technology of the variable speed drives today, which has matured significantly over the years, and we have incorporated a lot more controls. And I think and that is a Danfoss product, by the way, converted with more controls to be able to look at the pressure drop in the system, the drive, understanding, where the position of the pump is, looking at also the electrical load and the power consumed at that speed. We can calculate and look at what the flow of the pump is. So there's no need for transducers. The pumps can actually intelligently understand what the load is in the building, and match it accordingly. So that's, one of the methods for savings there.
And yeah, these are really cool products. And just to be clear, Armstrong was one of our partners on this project. So we had Peter Wolf, who was working with us from Armstrong, and he was in the presentation. And we had put this system together using Armstrong pumps that have Danfoss drives on them. And So we had not only a comprehensive system, but we had a comprehensive team working with us and with DGS on this project.
That's correct. The other part of it is that we're utilizing the ABQM, pick V valves, and so they're great in the fact that when we apply variable speed drives and we're going to vary the speed of the pumps, we inherently change the piping pressure that becomes more dynamic. And in a manual balancing valve, it's a fixed position so that when we change the flow, that valve doesn't react to the changes. What happens is that the flow either increases or decreases based on the characteristics of that valve. Where the difference between the ABQM is the fact that it is a dynamic valve and it's self-proportional and balancing. So when we have the changing pressures upstream of that valve in the system, that valve actually measures the differential pressure across the valve of the orifice opening within the valve. And if there's a change or drop, there's a diaphragm that reacts and either opens or closes the valve in response to the changes in the upstream pressure so that you get a constant flow of water out of it per the design and the requirements. So it's a great product. And we believe that's going to also save a significant amount of energy in the system.
And yeah, it's kind of funny. We talked a lot about this in the last episode, so please go back and listen if you want to hear more about the ABQM pressure independent control valves. But it is kind of funny because, we have this great chiller technology, variable speed modular, and these incredible variable speed pumps, which really can do a lot. But really the key piece of technology is this little valve that is modulating the flow into the coils and really allowing those big ticket items, the pumps and the chillers, to operate as they were supposed to. Because, if you can have the best variable speed chiller, the best variable speed pumps, but if you have these manual balancing valves and you don't have any control over the flow into the endpoints, the air handling units, you're really wasting those pieces of equipment.
That's correct. And, the heat transfer on the air side is dependent on the amount of flow that we provide to the coils. We have our delta T or heat transfer hydronically, but we also have the air over coil heat transfer that occurs. And if we overflow, we get a low delta T, which then impacts the chiller. And if we don't have enough flow, we have laminar conditions in the coil, which impede the heat transfer into the airstream. So the air handling units and the fans have to work twice as hard because they have to try to rotate even more air in that space to try to maintain the temperature.
Yeah, it's really about using as much water as is necessary, not overflowing, not underflowing, maintaining, the valves really allow everything to be used as it was designed. The chiller can maintain its proper delta T. The pumps can operate on the curve that they're set to. And the coils get as much water as they need to heat or cool that space, and no more, no less. So really what we discovered when we were putting this synchronized hydronic loop, program together it was really the valves that were kind of leading the project and allowing all the other technology to operate as it was supposed to be. And that's kind of how we designed our pitch and designed the program. And that's how this project ended up working, right?
That's correct. I mean, when we think about it, it's the building automation system which responds to the temperature in the space. And then that reaction to that space change is actually occurring at the coil in the fan coil unit, air handling unit, or VAVs with coils. And if we don't have the proper flow, then we're not going to have the proper heat transfer. And so it's very dependent on the end point for the other main components to react to that. So, when we look at that, we have the VAVs or the fan coil units that satisfy the space based on the proper flows. And then they'll shut off. And as they shut off, it creates back pressure against the pump for the pump to react, knowing that it needs to operate at more of a part load because we don't need as much flow. And then the response to the chiller or the boilers and other main equipment. So that's how, we have to look at this from a systems approach and how everything works in a symbiotic relationship to each other.
Yeah, very cool stuff. And I think this building is going to be working a lot better, and everybody will be much happier and much more comfortable. So where is the project right now?
We're about 3/4 of the way through. Most of the equipment is set in the mechanical room. We're waiting for some, minor equipment to still arrive. But we believe that within the next month or so, we should be ready to start up and commissioning the project.
Wow, that's awesome. Now, we're recording this at the end of June 2020. So I got to ask, has COVID and all that goes with it impacted this project at all?
Actually, it hasn't because of the fact that this project was a high priority for the state of Maryland. So, we've actually been moving pretty quickly on this project.
And I think what kind of worked in our favor here was that because the building was so kind of messed up to begin with, they evacuated the building and moved all the court's operations elsewhere, right?
That's correct. So there was another courthouse in Catonsville, Maryland, that they had just recently built. It was a new courthouse. So they managed to find other locations, and they actually moved the court cases to Catonsville. So they knew the importance of this building, so they actually shut it down, understanding that it would be a much faster process to get this done as opposed to trying to piecemeal this in phases.
Now, you mentioned that DGS is using this as kind of a blueprint going forward. Are there any more buildings in the portfolio that are dealing with similar issues that you're looking at now? How's that working?
Sure, there are other buildings that we're looking at. There were multiple buildings that we were considering at this time. Towson was the first. So it's going to probably set the standard. So the idea is to measure the energy savings over the next few years to see what they capture. And if it does save the energy that we expect it to, or that that we're expecting it to, then it could become the gold standard moving forward. There are other projects and state-run facilities that have similar issues. It hasn't come to a comprehensive look as we did for Towson, again, because part of it is that the significant amount of cost to fix these buildings properly with a comprehensive approach. So we're looking at this as a guide to some of these other projects moving forward.
Yeah, that's awesome. And I can't wait to see where that goes. Well, thanks, Jay, again for another great episode. And that's going to do it for this episode of the Envisioneering Exchange. I'd like to thank again Jay Chan, Director of Strategic Markets at Chesapeake Systems, for joining us again. And don't forget to subscribe to Envisioneering Exchange on Apple Podcasts, Spotify, SoundCloud, or wherever you listen to your podcasts. Lastly, if you enjoyed this episode, please don't forget to rate, review, and share with your network. It really helps us out. Again, I'm John Sheff, Director of Public and Industry Affairs at Danfoss, and thanks for listening, and we'll talk to you next time.